Different hearts, different dreams. Injective souls ignite the beams. No dream alone, no path ignored. Surjective wills knock every door. More hearts to thrive, or more dreams to grow. Two mighty sets now march toward battle. The wings of cardinality raise us high to the heaven of infinity, beyond the sky.
Previously, we discussed basic notions and examples of injectivity and surjectivity, along with how to write proofs based on their definitions. In this section, we introduce the notions of left inverse and right inverse, which provide alternative perspectives on studying injectivity and surjectivity. Let us begin with their definitions. Let f be a function from a set A to a set B. A function g from B to A is called a left inverse of f if the composition g after f is the identity function on A. In other words, if you take an element x in A, apply f to get some y in B, and then apply g to that y, you always return to the original x. The term left inverse is quite descriptive. In the composition g after f, the function g stands to the left of f, and we apply f first, then g. Similarly, a function h from B to A is called a right inverse of f if the composition f after h is the identity function on B. This means if you take an element y in B, apply h to get an element x in A, and then apply f to that x, you return to the original y. Again, the term right inverse reflects that the function h is to the right of f, and we apply h first, followed by f. Regardless of whether we are talking about a left or right inverse, the domain and codomain of the inverse function should be the reverse of those of f. The key difference lies in the order of composition and the resulting identity function. Let us study some examples. Let f be the function from the set of non-negative real numbers to the set of real numbers, defined by fx equals x squared. Now, we define a function g from the set of real numbers to the set of non-negative real numbers as follows. When y is greater than or equal to 0, gy is equal to the square root of y. When y is negative, gy is defined to be 1 uniformly. We can verify that for every x which is non-negative, g of f of x equals g of x squared. Since x squared is always greater than or equal to 0, we use the first case in the definition of g, taking the square root, which gives us back x. Hence, g is a left inverse of f. We remind the reader that the left inverse of such a function f is not unique. Indeed, take a look at the second part of the definition, where negative values of y are sent to 1. We could redefine this part and send negative y values to 2 instead. One can easily verify that this new function g still serves as a left inverse of f. After all, when you start from an element in the domain of f and apply f, you end up with a non-negative number. Then, when you apply g, you are always using the first case in the definition. So it doesn't matter how we define gy for negative y, as those values are never actually used in the composition. On the other hand, f does not admit any right inverse. If it did, then starting from a negative y, applying a right inverse h would give some non-negative x, and applying f to that x would have to return y. But fx is always non-negative, so it could never return a negative y. Hence, such an h cannot exist. Let us consider a similar example, but with the domain and codomain reversed. Let f be the function from the set of real numbers to the set of non-negative real numbers, defined by fx equals x squared. Now, we define a function h from the set of non-negative real numbers to the set of real numbers, given by h of y equals the square root of y. Then, for every non-negative y, we have fhy is equal to the square of the square root of y, which is equal to y. Hence, h is a right inverse of f. We emphasize that the right inverse of f is not unique. For each non-negative y, one could have defined hy to be either the square root of y or the negative square root of y. Both would still satisfy fhy equals y, and thus also serve as a valid right inverse. So, there are infinitely many ways to define a valid right inverse h in this context. On the other hand, f does not admit any left inverse. Otherwise, assume that g is the left inverse of f. We would have gfx equals x for all real x. But since fx equals x squared maps both x and minus x to the same element, there is no way to define a single-valued function g that correctly recovers x and minus x at the same time. Therefore, no left inverse exists for f. You have now seen what a left inverse and a right inverse are. The previous examples suggest a connection between being injective and having a left inverse, and similarly, between being surjective and having a right inverse. We will explore these relationships in more detail in the sections to come.
신라 텐세